Welcome to day 36, the future of programming languages. Today we will explore predictions, trends, and the challenges facing the evolution of programming languages. Let's dive in. In this session, we will focus on several key topics: predictions for language evolution, the role of machine learning and AI in language design, emerging paradigms and features, the impact of new technologies, and ethical considerations. We will also look at the challenges and opportunities for language development in the future. As we look to the future, we can expect increased abstraction in programming languages, making them easier to learn and use. Domain-specific languages (DSLs) will rise in popularity, catering to specific industries, while cross-platform development will see languages like Kotlin and Rust lead the charge. Furthermore, machine learning will begin to play a significant role in optimizing code and enhancing the programming experience. Machine learning and AI are poised to revolutionize programming languages. In compiler design, AI will help auto-tune code for hardware efficiency. Additionally, AI-powered tools like codecs will assist in code generation, while real-time bug detection and intelligent debugging will make coding faster and more reliable. The next generation of programming languages will introduce features such as AI-driven programming, enabling the creation of languages tailored for machine learning. We will also see self-optimizing languages that automatically enhance their own performance during runtime. Concurrency and parallelism will be simplified, and specialized languages for quantum computing will begin to emerge. New technologies will have a profound impact on language design. Blockchain will influence languages like Solidity for decentralized applications. Cloud-native programming languages will be optimized for cloud environments, while languages for VR/AR development will evolve to handle 3D object manipulation. Languages will also be tailored for edge computing, enabling more efficient distributed systems to IoT applications. Ethical corners will play an increasingly important role in the development of programming languages. Designers will need to focus on privacy, security, and inclusivity, making languages accessible to a broader range of users, including those with disabilities, and considering the cultural impact of programming languages will be critical for ensuring that technology remains beneficial for all. The development of new programming languages will face several challenges such as maintaining backward compatibility with older versions. Security concerns must also be addressed, ensuring that new languages are resistant to vulnerabilities. However, these challenges present unique opportunities to innovate, particularly with AI-driven security and language optimizations. As programming languages evolve, so too will the role of developers. The future will see a shift from coding syntax to high-level program problem solving and application design. Developers will focus more on logic and abstract design rather than dealing with low-level details. Continuous learning will be essential as new languages and tools emerge in response to technological advancements. To recap, key trends in programming languages include the rise of AI and cloud native development, the growing importance of specialized paradigms, and a focus on security and ethics. These trends will shape the future of software development and how we interact with technology. In conclusion, the future of programming languages keeps promising with new advancements on the horizon. As developers, it's important to stay updated on emerging trends, participate in the design of new languages, and be ready to adapt to new technologies as they arrive. Thank you for joining me in this session. Now, I would love to hear your thoughts and answer any questions you may have. Please feel free to ask anything related to the topics we have covered today. Welcome to the Language Design Project. In this session, we will explore a practical approach to designing a new programming language. Let's dive in and learn how we can create a language from scratch. Today, our objective is to design a new programming language focusing on the syntax, semantics, and basic features. This hands-on experience will help you apply the concepts you have learned throughout the course in a real-world context. Why would you want to design a language? By understanding the trade-offs in language design, we can better appreciate the thought process behind popular languages. We will also look at the challenges faced by language creators and how their solutions impact software development. Language design involves several key steps. First, we define the purpose of the language. Then we design the syntax and structure of the language. Finally, we define the semantics, how our constructs will behave and interact with the system. Let's break this down further. The first step is to define the purpose of your language. What problem will it solve? Is it a general purpose language or a domain specific language focused on a particular application like web development or scientific computing? Understanding the target audience is crucial here. Next, we move on to designing the syntax. This includes defining the structure of valid statements and expressions. Will your language be case sensitive? Will it use indentation like Python or braces in C? Think about how control structures like loops and conditionals will look in your language. Once the syntax is defined, the next step is to focus on semantics. This is about determining what each construct in your language means. How will loops behave? What's the memory model of your language? Will it use automatic garbage collection or will the programmer manage memory manually? Now let's think about the key features of your language. What paradigms will it support? Is it imperative, functional, or object oriented? What features will make your language unique and stand out from the rest? Designing a language involves using several tools and frameworks. You will need to create a prototype using an interpreter or a framework. There are also tools like Antler or Lex and Yak to help the parsing process. Once the language is designed, documenting its grammar, syntax, and semantic is essential. Now it's time for the practical exercise. You will be working either individually or in small teams to design a programming language. You will need to focus on defining the purpose, syntax, and semantics of your language. Keep in mind the trade-offs in language design. After completing your design, you will share your language with the class. You will discuss the rationale behind your decisions, such as why you chose a particular syntax or memory model. It's a great opportunity to learn from each other and get feedback. As we wrap up, we will have an open Q&A session to discuss any challenges you faced during the design process. We will also review how different programming paradigms influence the way we design languages. You will gain a deeper understanding of the language design process. For your assignment, you will submit a language specification document. This document should include your language purpose, syntax, grammar, and semantics. Be sure to outline key features and any innovative aspects of your language. Thank you for your attention today. If you have any questions, feel free to ask. Remember, designing a language is an exciting and challenging task that requires creativity and deep understanding of programming concepts. Best of luck for your projects. Welcome to today's session on language case studies. In this presentation, we will explore real-world examples of programming languages, their design decisions, and their impact on software development. Let's dive in. Today, we aim to dive deeper into real-world examples of programming languages. We will explore how different languages have evolved over time, learn from their successes and failures, and understand the design and applications of some of the most popular programming languages. Language case studies are essential as they provide insights into how theoretical language design meets practical application. By analyzing successful and unsuccessful languages, we gain a better understanding of the decisions made during their design and the trade-offs involved in language development. Our first case study is C, one of the most influential languages in the history of computing. Designed for system-level programming, C emphasizes performance and control over hardware. Its strengths lie in its simplicity, portability, and efficiency. However, it lacks built-in safety features and manual memory management can lead to errors. C has been crucial in operating systems, embedded systems, and hardware programming. Next, we have Python, a high-level interpreted language known for its readability and ease of use. Python has become the go-to language for beginners due to its simple syntax and vast library support. While it's slower than compiled languages and relies on dynamic typing, its real-world applications are vast, from web development to data science, AI, and automation. Java, designed for portability with the Java Virtual Machine (JVM), follows an object-oriented paradigm. Its strengths include robust memory management, a rich library ecosystem, and cross-platform capability. However, its syntax is often seen as verbose and it tends to be slower than languages like C and Go. Java remains widely used in enterprise applications, Android development, and large-scale systems. Rust is a systems programming language that prioritizes memory safety without sacrificing performance. Its strength lies in preventing memory errors like null pointer dereferencing and buffer overflows, thanks to its ownership model. While Rust's learning curve can be steep, it's well suited for performance critical applications, WebAssembly, and embedded systems. Go or Golang was designed for simplicity and high developer productivity, focusing on concurrency and ease of use. It offers a simple syntax, fast compilation times, and built-in concurrency via Go routines. Despite its strengths, Go lacks generics and a more extensive standard library. It's popular for cloud computing, backend systems, and microservices. In this slide, we compare the case studies we have discussed. We will see that each language design decisions are influenced by different priorities: performance versus productivity, memory safety versus control, and cross-platform compatibility. Rust and Go are modern languages addressing limitations of older languages like C and Java, bringing new concurrency models and memory safety features. Now it's your turn. For this exercise, choose one of the languages discussed today and justify its best use cases based on its design features. Additionally, consider which language would be the best fit for a specific domain such as systems programming or web development. Feel free to discuss your thoughts with your peers. Programming languages have a long-term impact on industries, software development practices, and the overall tech ecosystem. By understanding the real-world applications of these languages, we can make informed decisions about which language to use in different contexts. To conclude, understanding the history, strengths, and weaknesses of programming languages helps us become better developers. Today, we have covered the key takeaways from our case studies, from language design decisions to real world applications. I encourage you to explore further and experiment with different languages to deepen your understanding. That brings us to the end of today's presentation. I would like I would now like to open the floor for any questions or feedback you may have. Feel free to ask about the case studies, language features, or anything else related to programming languages. Welcome to today's presentation on ethical and social considerations in language design. In this section, we will explore the importance of ethics in programming languages, their social impact, and how developers can contribute to responsible language design. Let's dive into how programming languages influence both society and the development community. Ethics in programming is about understanding the moral implications of the languages we create and use. Ethical considerations play a key role in how programming languages are designed, influencing both society and developers. By considering these ethics, we can promote responsible design that benefits the greater good. Let's take a closer look at why this is so important. Inclusivity is a fundamental aspect of modern language design. We must ensure that programming languages are accessible to a wide range of users, including those with disabilities. This also involves supporting multiple languages and character sets for global use. Additionally, gender-neutral language promotes equality in our code, ensuring that terminology is inclusive for all programmers. Programming languages can inevitably introduce ethical dilemmas, especially when it comes to security and privacy. For example, certain language features may create vulnerabilities, allowing malicious actors to exploit weaknesses. Bias in language design can also affect fairness, particularly in AI and machine learning applications. It's essential that developers recognize and address these ethical issues to create more secure and equitable languages. The impact of language design goes beyond technical features. It also affects developers and users. Developers must take responsibility for the languages they design, ensuring that they promote transparency and fairness. The choice of language can also impact job opportunities, as some languages are more widely adopted than others. Lastly, programming education plays a crucial role in shaping how developers understand and implement ethical considerations in their work. Programming languages don't just affect code quality, they also have environmental implications. Energy efficiency in language design can reduce the computational power required to run applications, which is particularly important in resource-constrained environments like IoT devices. As software development practices evolve, we must also consider sustainability and the ecological footprint of our programming decisions. As programming languages evolve, we face important ethical decisions such as whether to prioritize open source development or proprietary systems. Open source languages foster collaboration and transparency, while proprietary languages may limit access and innovation. The process of language evolution often involves addressing challenges from older systems and integrating new paradigms, requiring careful ethical considerations. An ethical review process is crucial for ensuring that new languages are designed with moral responsibility in mind. Ethical committees can guide language developers in identifying and addressing potential issues such as biases or harmful constructs. Case studies of languages that have faced ethical scrutiny can provide valuable lessons for future language design. The importance of ethical considerations in programming languages will only continue to grow. As new technologies emerge, such as AI and machine learning, they will introduce new challenges for language designers. Developers must stay aware of these issues and work towards solutions that prioritize fairness, transparency, and social responsibility. The future of language design lies in its ability to adapt to the ethical demands of our rapidly evolving world. Thank you for your attention. If you have any questions or would like to discuss any of these topics further, feel free to reach out. I am happy to answer any queries you may have. Remember, responsible programming language design can help shape a better future for everyone in the development community and beyond. Welcome to the presentation on the challenges in modern language development. Today we will explore some of the key issues in programming language design and development, as well as their future directions. In this presentation, we will provide an overview of the key challenges in programming language development. We will discuss how languages evolve to meet the demands of new paradigms, hardware advancements, and security concerns. One of the major challenges in modern language development is ensuring backward compatibility. As new versions of a language are released, they must support old code to avoid breaking existing applications. Some strategies used to maintain compatibility include deprecation, versioning, and maintaining compatibility layers. However, managing legacy code like COBOL or Fortran remains a challenge for many organizations. As programming languages evolve, there's an increasing need to integrate multiple programming paradigms such as imperative, object-oriented, functional, and concurrent programming into a single language. This integration presents challenges including cognitive overload for developers and maintaining simplicity. Languages like Scala, C++, and Rust have made strides in this area by supporting multiple paradigms. Security is a critical concern in modern language development. Languages must include features that prevent vulnerabilities like buffer overflows and SQL injections. For example, Rust provides memory safety with its ownership and borrowing system. Modern languages also address security through features like sandboxing and execution models, ensuring safer execution environments. Concurrency and multithreading present significant challenges in language design. Race conditions, deadlocks, and ensuring thread safety are common issues. Modern languages like Go and Java have introduced models like Go routines and threads to manage concurrency. However, balancing efficient concurrency models while avoiding complexity remains an ongoing challenge. Hardware advancements such as the rise of multi-core processors and GPUs have influenced language design. For example, languages like CUDA have been developed to utilize GPU capabilities. However, the challenge is to balance performance optimization with portability. Languages must evolve to make the most of new hardware while remaining compatible across different platforms. Another key challenge is maintaining a balance between developer productivity and performance. High-level abstractions often improve productivity, but they can come at the cost of performance. For example, languages like Rust prioritize performance without sacrificing developer safety. Striking the right balance is essential for creating languages that are both efficient and easy to work with. To recap, we have discussed several key challenges in modern language development, including backward compatibility, the integration of old and new paradigms, security, concurrency, hardware adoption, and balancing productivity with performance. These challenges shape the evolution of programming languages. Looking forward, we expect programming languages to continue evolving in response to new needs and emerging technologies. The integration of AI and machine learning in language design will likely bring new paradigms and capabilities. However, ongoing challenges related to complexity, security, and performance will remain key considerations in the development of future languages. Thank you for your attention. If you have any questions or feedback, feel free to ask. I would love to hear your thoughts on this topic. Welcome to Day 41, a review of key concepts in the Principles of Programming Languages course. Today we will be summarizing the major topics we have covered throughout the course and preparing for our final wrap-up. Let's begin by reviewing the major topics we have explored. First, we have discussed the foundational concepts of syntax and semantics and how these shape the structure and meaning of programming languages. We then dove into types and type systems, looking at the differences between strong and weak typing and static versus dynamic typing. Memory and variables were also key aspects we studied, including stack versus heap memory and the importance of garbage collection. We also covered control structures like recursion, loops, and conditionals, as well as the different programming paradigms, including imperative, declarative, and object-oriented programming. Now let's shift focus to language design and implementation. We looked at the role of language design, how compilers versus interpreters work, and the different phases of language implementation, from lexical analysis to code generation. We also discussed how runtime systems such as JVM and CLR manage memory and execute code. Next, we reviewed two critical areas of programming: error handling and concurrency. We explored the different types of errors, syntax, runtime, and logical, and how exceptions are handled in languages like Java, Python, and C++. On the concurrency front, we delved into how modern languages manage threads, processes, synchronization, and potential issues like deadlock. Moving on to the advanced features found in modern languages, we explored coroutines and the async await pattern for asynchronous programming. We also covered metaprogramming, where code can modify itself, and reflection and introspection, which allow a program to examine its own structure. This is the perfect time for an open Q&A session. If there's anything you would like to clarify about key concepts like memory management, programming paradigms, or error handling, feel free to ask. Let's dive into any lingering questions you may have. Let's take a moment for a group discussion. Think about how the concepts we have learned today apply in real world scenarios. How do different languages handle memory management and concurrency? How do you select the right language for a project based on its strengths and weaknesses? We have certainly encountered challenges during this course. Some of the major ones include debugging in dynamic versus static languages and managing concurrency in multi-threaded environments. Today we will discuss some practical solutions to these challenges that will help you in your programming journey. As we wrap up, here are the final takeaways. The importance of abstraction, modularity, and efficiency has been evident through the course. You should now have a deeper understanding of memory management, type systems, control structures, and the impact of different programming languages on software design. The key to success in programming is continually applying these concepts and choosing the right tools for the task. Don't stop here. Continue your journey with additional resources for further learning. There are numerous books, online courses, and practice platforms such as LeetCode, HackerRank, and CodeWords that will help you strengthen your knowledge and skills. Keep challenging yourself with new problems and languages. Finally, we have reached the course wrap up. Reflect on the path we have taken, the skills you have gained, and the concepts that will shape your future programming projects. We have covered a wide range of topics that prepare you for careers in language design, software development, and more. Keep exploring and thank you for participation in this course. Welcome to day 42 of the Principles of Programming Languages course. In today's session, we will recap key concepts, explore future learning paths, and discuss career opportunities related to programming languages. Let's begin by revisiting the major topics we have covered in this course. We explored syntax and semantics, diving into how structure and meaning work in programming languages. We also learned about various programming paradigms such as imperative, functional, and object-oriented programming. We examined type systems, memory management techniques, and key language implementation concepts like lexical analysis and code generation. Additionally, we explored concurrency, parallelism, and modern programming features like async, await, and meta-programming. Before moving forward, we will take some time for a Q&A session. Feel free to ask any questions, engineering, or clarify any concepts that you might have found challenging. This is your chance to review topics that may need more attention, such as the differences between static and dynamic typing, or how paradigms like functional and object-oriented programming can impact code design. As you continue your journey in programming languages, here are some resources to further deepen your knowledge. Books such as Concepts of Programming Languages by Robert W. Sebasta and Programming Language Pragmatics by Michael L. Scott are excellent reads. Online platforms like Coursera, edX, and Udacity offer courses to continue your learning. Additionally, academic papers from conferences like POPL and journals from ACM, SIGPlan can provide cutting-edge research in the field. To practice what we have learned, consider using tools like GCC for C, C++, JVM for Java, or Haskell's GHC for functional languages. Online IDEs like REPL.it and Glitch offer easy access to scripting languages like Python and JavaScript. And practice platforms such as HackerRank, LeetCode, and CodeWords are fantastic for honoring your problem-solving skills and learning new concepts in a hands-on way. Programming languages open up a variety of career paths. As a software developer or engineer, you will be working with languages to develop everything from backend systems to front-end interfaces. If you are interested in language creation, you can pursue a career as a compiler engineer or language designer. There's also the option to work as a researcher, contributing to new theories and advancements in programming languages. Another option is software architecture, where you will apply your language knowledge to design scalable systems. Let's reflect on the course. We have covered a wide array of topics that give you a strong foundation in understanding how programming languages work. Moving forward, I encourage you to keep experimenting with different languages and paradigms. Your feedback is also incredibly valuable. Please share your thoughts on how this course can be improved or topics you would like to explore further. As we wrap up, I want to leave you with a motivational quote. The more you learn, the more you realize how much there is to discover. Programming languages are vast, and there's always more to learn. Keep staying curious and apply your knowledge to solve real world problems. Thank you all for your participation, and I wish you all the best in your future programming endeavors. Before we conclude, are there any final questions? This is your chance to clear up any doubts or share your thoughts about the course. I am here to help and address any lingering questions you may have.